This conference will now be recorded.
Hello everyone. So the first slide here you can see the uses of carbon monoxide. So we will we'll start with this slide, and after that there will be discussion related to the another oxide of carbon, which is carbon dioxide. So once carbon dioxide is finished, then important compounds of silicon we will start to discuss, and there will be related problems. So carbon monoxide, we have seen its structural features, how we can prepare it, and important properties. Now, what are the applications for this monoxide of carbon? Important constituent of two industrial fuels, that is water gas and producer gas. So water gas, it is mixed with H2, and in case of producer gas, it is mixed with nitrogen. And in case of Mons process for purification of nickel. So in Mons process, what we do, suppose we have some impure nickel. So first we treat it with CO, and there is formation of nickel tetracarbonyl. Now once nickel tetracarbonyl is formed, then we heat it at temperature 450 to 470 Kelvin, and the first step temperature, this is to some extent lower. So when we are making this complex of nickel, that is nickel tetracarbonyl, then the temperature is 330 to 350. And when we are, once the complex is formed, then if we are again heating it, so why we are doing the reverse process now? Because we want to get pure nickel. So in this case, we get pure nickel by decomposition of this nickel tetracarbonyl. And this is also, you can say another way, that it is by this method we can also produce pure carbon monoxide. But this process is mainly for formation of pure nickel. So this is the application of carbon monoxide. Then as a reducing agent to many metal oxides to convert them to metals, and specifically this application is related to metallurgy, where for minerals or ores of metals we recover the metals in the elemental form, that is the metallic form. So when we have the metallic oxide, the metal, it is in some oxidation state, maybe 2+ or 3+. Suppose I am writing here Mn+ oxidation state. Now in presence of CO, this M will be converted to metallic state, that is 0 oxidation state. So here what is the role of CO? CO is basically acting as reducing agent. It is providing electrons to Mn+. Okay. So in this way, we can use it as a reducing agent in metallurgy. Then in manufacture of methyl alcohol, acetic acid, you can see here different organic compounds are there. So for the source of group CO, C double bond O, for this group we use CO, this carbon monoxide. Then some other applications, infrared laser to remove rust from surface of metals, in some beverages and food to acidify them. Important ligand for formation of metal carbonyl complexes, because in the properties part of CO we have seen how it is so versatile when it reacts with metals in 0 oxidation state. There are a variety of metal carbonyl complexes. So there is a separate chemistry, that is these compounds are so versatile and having so important characteristic that there is separate chemistry for metal carbonyl complexes. One of the reagents for production of aldehydes. So sometimes when we have some alkene, suppose we have alkene RCH double bond CH2, then in presence of CO and hydrogen gas, we can make RCH2CH2, CH. Sorry, this one carbon extra. So here, for formation of aldehyde starting from alkene, one of the reagent is we are using carbon monoxide. One of the reagent, because other reagent is H2. So here the CO part of, that is the carbonyl group in CHO, that the source of this group is carbon monoxide. So these are the different applications of carbon monoxide. So here, sorry, this is a full question. So it is related to carbon monoxide structural features related question. Which of the following statement is correct for carbon monoxide? So in the structural section of carbon monoxide, we have seen what is the hybridization of carbon and oxygen, what are the different types of bonds present between carbon and oxygen. So here we have different options. The first option is saying that there is a double bond present between carbon and oxygen. Then 1 sigma, 1 pi, and 1 coordinate bond between carbon and oxygen. 1 lone pair of electrons only on oxygen. Now, if you look at the structure, you can see there is lone pair present both on carbon as well as oxygen. So this statement is obviously not true. This is false. 1 sigma 2 pi. So the triple bond that we that is draw carbon monoxide molecule in this way, here actually one bond is sigma bond, one bond is pi bond, another bond is coordinate bond. Okay, so here you can see this bond as if it is sigma bond, then the next bond is pi bond, and this arrow sign that we use for coordinate bond that you can see in the third step. So details we have already seen in the structural features, that is in the last class we have discussed it. So I'm not going details into the discussion because otherwise same thing will be repeated. Fine. So remember the triple bond that we see, one of these bond is sigma bond, where one electron is coming from carbon, as you can understand from this picture. Here this black electron that is coming from carbon and the blue one that is coming from oxygen. Then for the pi bond, which is by the pure p orbital, here hybrid orbitals are not used. So the second bond, that is pi bond, here also one electron coming from carbon, another one is coming from oxygen. But the last one, which is coordinate bond, both the electrons are coming from oxygen, which is clear from the color because both the electrons are in blue. And these two electrons are not used for bond formation. So carbon is also having 2 electrons and it is remaining as pair, which is lone pair. So lone pair is present on both. So the first statement, a double bond between carbon and oxygen, it is not double bond. There is actually total 3 bonds. So this is also not correct. This B option is correct. Third one is not correct. One lone pair of electrons only on oxygen, but it is not only on oxygen. On carbon also there is no. And the last one, 1 sigma 2 pi, this is also not correct. Okay, so only the second statement is correct. Next question, that is also related to carbon monoxide. A very pure form of carbon monoxide can be obtained from sodium hexacyanoferrate, sodium oxalate, formic acid, nickel tetracarbonyl. So remember, just we have seen in the application slide, that is the first slide today's class. There we have seen how starting from nickel and CO at 350 to 330 to 350 Kelvin temperature, first we are making nickel tetracarbonyl complexes and then we are heating it. Now for the second time, temperature is very high, we are decomposing this complex again and here we get pure nickel. But remember, this is also, you can say, a method for formation of pure carbon monoxide. So here both these compounds we are getting in pure form. So this is actually Mons process, which is mainly focused on nickel, but we can also make pure form of carbon monoxide. So this one will be, that is the last option will be the correct option, not the other three, that is sodium oxalate or formic acid or sodium hexacyanoferrate. When carbon monoxide is passed over solid caustic soda, we have not taken the solution of it. So caustic soda means NaOH in solid form and heated up to 200 degrees centigrade, it forms what? So NaOH, when it reacts with CO, it forms HCOONa, that is sodium formate. Formic acid is HCOOH. Now in this formic acid, if you simply remove this H part and here if we write Na, then this is actually this one. So this is a reaction between these two compounds CO and NaOH at temperature 5 to 10 atmosphere, 120 to 200 degrees centigrade, and there is presence of catalyst also. So we are getting this one, that is option C. It is not sodium carbonate, it is not NaHCO3, it is not sodium acetate, because see, the last one, this compound formation is not possible because here it is sodium salt of acetic acid and we have total 2 carbon, right? So here we are using only CO, which is source of only single carbon. So this cannot be the correct option. Okay. Next. So once that is the first oxide of carbon, which is carbon monoxide, we have completed it. Now we will start carbon dioxide. So in carbon dioxide, this is linear structure, two sides of carbon, there is two double bonded oxygen. First we will see how we can prepare it, how we can prepare this oxide. Here also we will use oxidation reaction. Now oxidation of what? You can oxidize carbon, that is you can burn carbon or some fossil fuel. Now when we are talking about fossil fuel, it means some hydrocarbon. So you can see here in the second equation it is methane, which is hydrocarbon, then C5H12. So both these are basically alkane. If you follow the formula CnH2n plus 2. So n value if you consider 5, then 2n plus 2 will be 12. Similarly in if it is 1, then it is methane, CH4. So in this case, we are using excess of air or oxygen. In the previous oxide, that is carbon monoxide, there we have seen we are doing the controlled oxidation. That is in lack, that is not excess of oxygen. Because if excess of oxygen, there will be formation of CO2. But when we want to make CO only, there should not be excess of air. But now we want to make CO2. So that is why we have to take excess air or excess oxygen. Okay, so in all these reactions there is formation of CO2. Only when we have taken hydrocarbon, the second and third equation, now we are also getting water as byproduct, but this is our main desired product. In laboratory scale, that is a small scale, how we can make it? So CO2 is prepared in laboratory by the action of dilute hydrochloric acid on some metal carbonate. So here if you look at this picture, there is some marble chips, which is nothing but calcium carbonate that is taken here, and here we have some dilute HCl. Now we can control with this stopcock, and there will be dropwise HCl that will be in contact with calcium carbonate, and there will be formation of CaCl2, H2 and CO2. Now CO2 being a gas, it will be going through this tube and it will be collected like this, where you can see here we have water trough and carbon dioxide gas that is deposited here. Okay. There is one more method which is a large scale method, that is commercial scale. So when this commercial scale, now we will again use calcium carbonate or we can use magnesium carbonate. But now we are not using any other reagent, it is simply we are heating it. So it is decomposition of CaCO3 or MgCO3, and in both cases you can see the reactions are same because Mg and Ca both are group 2, so their behavior is alike. Calcium oxide we are getting as byproduct, here magnesium oxide, but actual product is that we are trying to make is carbon dioxide. Okay. So after preparation of carbon dioxide, next we have to see its structure. Now when it is carbon monoxide, we have seen the hybridization, it is sp, but now carbon is sp, but oxygen is sp2, right? So carbon is sp, oxygen is sp2, and it is linear, and dipole moment is 0. And dipole moment is obviously expected 0 because it is linear, and oxygen both sides there is similar type of bond. So if you consider the direction of dipole moment, the left hand side direction that will be cancelled by the right hand side. Fine. Now how to that is explain this bonding? Here if I for carbon, as it is sp hybridized, so there will be 2 sp and 2 p orbitals that will remain as pure p orbital. And here total 4 valence electrons I will draw like this. Now what about oxygen? So when it is oxygen, it is sp2 hybridized, so there will be total 3 sp2 hybrid orbital and 1 p orbital, that is pure p orbital. For oxygen there is total 2s2 2p4, that means total 6 electrons, right? Now in sp2 there will be 1, here lone pair, this is also lone pair, 1 more electron here. Now if you consider the bond, carbon, this is for carbon, this is for oxygen. So carbon will use one sp and to form sigma bond with oxygen. So this will be used for sigma bond. Now these two are lone pair for oxygen, because for each oxygen there is two lone pairs. Whether you consider the left hand side oxygen or right hand side, both are actually in similar chemical environment, right? And the electron that is present in pure P for carbon, so this will be used for pi bond formation. Now carbon, it is also having another sp, so it will use it for sigma bond formation with another oxygen atom, and this pure p orbital, this electron, that will also be used for another pi bond formation with another oxygen. So in this way you can understand the hybridization, and there is sigma bond, one sigma bond, and y pi bond both sides. Okay, no coordinate form. Now if you look at this orbital picture, here we have carbon in the central position, and this is sp hybridized, that we know. Now one sp it is using for bond formation, so this is sigma bond, obviously here also sigma, and this is lateral overlap. So this is pure p orbital, it is lateral overlap, another pure p orbital of oxygen. These two are lone pair. Now lone pair of electrons that is placed in sp2 hybrid orbital of oxygen, that you have already seen in the previous diagram. That is the two lone pairs. They are residing in sp2. So why these details are required? So suppose you are getting a question where it is mentioned that lone pair is residing in which orbital? Is it sp3 or sp2 or pure sp orbital? So to answer this question, we should know whether that is lone pair is residing in what type of orbital. Okay, so it is sp2 hybrid orbital. So same thing is also for the other oxygen, because both are in similar chemical environment. So this sigma bond is formed. The sp is coming from carbon, but sp2 is coming from oxygen. So that is, it is sp2 sigma bond. And pi bond, that is always whenever pi bond is there, it will be always with pure p orbital, never with hybrid orbital. Now we have this explanation. Two sp hybridized orbitals of carbon overlap with two separate oxygen. They are sp2 orbitals to make two sigma bonds both sides, while the other two electrons of carbon are involved in pi bonding with oxygen. So that you can see here. So these two are involved in pi bond formation. Both the carbon and oxygen bond length should be equal, because if it is C double bond O both sides, so it is expected that it will be equal. But what happens? There is some resonance going on. Because of this resonance, there is some triple bond type of character generation. So see what is happening. If the left hand side oxygen, if it is using a lone pair and it is making a triple bond between carbon and oxygen, now it will acquire some positive charge, and this double bond will be broken and negative charge over oxygen. Same thing can also occur from right hand side, that is like this. Now you can see there is some triple bond type of character generated between oxygen and carbon. So that is why the value of bond length should be a typical bond length of C double bond O, which is around 122 picometer. That is expected. But experimentally, we are seeing something different. What we are seeing? We are seeing that it is 115 picometer, and it is because of resonance. So if you consider these two structures of resonance, though the first one is more stable, but if you consider the other two resonance structure, then there is some triple bond character, and whenever there is triple bond character, the bond length will be slightly lesser than 122 picometer. So now it is 115 picometer. Fine. Now we will start properties of carbon dioxide. If we consider the physical property, it is colorless, non-flammable. So it will not support burning process, and 1.5 times heavier than air. Actually, see, this is because of this particular property, it is 1.5 times heavier than air. So that is why it helps to that is, it can be used as a fire extinguisher, because as it is heavier, it can remove oxygen, and when oxygen will be removed and that place will be taken by CO2, now burning process will be inhibited. Okay, so that is why it is not supporter of burning process. Critical temperature is 31 degrees centigrade. So critical temperature is that temperature beyond which we cannot do any liquefaction for gas. For every gas there is a critical temperature. Now for CO2, as the value is 31 degrees centigrade, that means if you consider room temperature or 20 or 25 temperature, you can easily liquefy it. Because if the critical temperature is suppose 10 degree or 15 degree, then beyond it we cannot do liquefaction. Then we have to lower the temperature. But in this case, we don't have to maintain any special condition because it is already high. It is already 31 degrees centigrade. And if you are below this temperature, you can easily liquefy this gas. Okay. So it is easily liquefiable gas. It is neither combustible nor a supporter of combustion. So the logic I have already mentioned. Why? Because it is 1.5 times heavier. First of all, it is not combustible, and second thing is it is not also supporter of combustion. Fine. It is a very stable compound, because if you consider the structure, if you want to decompose it, or if it has to take part in reaction, then the double bonds between carbon oxygen, two double bonds has to be broken, and that is difficult process. So that is why it is stable compound even at 3100 Kelvin. This is very high temperature, 3100 Kelvin, very high temperature. So even at this temperature, only 76% can be decomposed to carbon monoxide and oxygen gas. And if it is still higher temperature, then it is possible to decompose it to carbon and oxygen. Solubility in water. Solubility of CO2 in water is low, 3.48 gram per liter. Now this solubility, you have to maintain the conditions, obviously, that is, you have to mention the temperature, the pressure. So it is at 0 degrees centigrade at 1 atmosphere. But if you change the condition, suppose you are increasing the pressure, then obviously solubility will increase. So solubility can be increased with increase in pressure, but with temperature, now the relationship is reverse. If you increase temperature, now it will decrease. So with pressure it will increase, but with temperature it will decrease. Most of the dissolved CO2 remains loosely hydrated. So CO2, that is the part of CO2 which is already dissolved in water, they will remain loosely hydrated. Now, the low solubility in water, that is actually immensely helpful from the point of view of biochemistry, or if you consider geochemical importance. So its low solubility actually helps in some processes that is important for some biochemical reactions or some geochemical reactions. So this property is actually helping us. Fine. Chemical properties. Now, as it can be, that is, though it is low soluble, but it can be dissolved in water. And when it reacts with water, that is, actual reaction is happening, not loosely bound. When there is actual reaction with water between, that is, CO2 and water, then there is formation of H2CO3. So this is carbonic acid. Now this acid is very weak acid. Its acidity is not very high, not like HCl or H2SO4. This is a very weak acid. And as it is weak acid, and also see, there is two replaceable hydrogen. So it is diabasic acid also. So it is weak diabasic acid. And it can form two series of salts. And these salts you have already seen in case of alkali metals and alkaline earth metals. So now you will understand that where from those anions, suppose I am saying Na2CO3, sodium carbonate, that we have seen in case of S block chapter in group 1, or I am saying NaHCO3. So where from this is coming? That is, if you consider the anion, here the anion is CO3 2 minus, here the anion is HCO3 2 minus. So both these anions, the source is same, the source is H2CO3. So if H2CO3 it is ionizing as H plus, that is only one hydrogen is dissociated from H2CO3, then the anionic part is HCO3 minus. So if you are considering this dissociation, then the corresponding salt from this bicarbonate anion, this anion is called bicarbonate, or another name is also there, hydrogen carbonate. So hydrogen carbonate salt is NaHCO3 or KHCO3 like this. But if you that is further consider the second dissociation, now this H is also removed. Now we are getting the anion carbonate CO3 2 minus, that you can see in sodium carbonate or K2CO3, that is potassium carbonate. Okay, so these two series of salts can be produced. So a solution of CO2 in water, if we consider, there is equilibrium of these four species. So total four species you can find when you consider the water solution. There is equilibrium between all these species. So why there is equilibrium? Because it is not very strong acid. So the dissociation will be there, but mostly it will remain in undissociated condition. If you look at the value of its dissociation constant, then it will be more clear. It is not very high, so don't expect it like HCl or H2SO4, where it is 100% dissociated condition in water medium. But now it is not so. So that is why there will be all these four species. So how all these four species? H2CO3, because you are starting with this, and H2CO3 it will remain in undissociated state. So H2CO3 will be there. Then CO2 will also be there, because H2CO3 you are getting starting from CO2 and water. So CO2 will be there, H2CO3 will also be there. Once H2CO3 is formed, then further dissociation that will lead to these two species. But that doesn't mean that all the H2CO3 molecules are dissociated. No, it is not that. So all these species, and obviously water will be there, that is not mentioned here because we are just focusing on the carbon related compounds. So remember, in the equilibrium mixture, all these four species you will get. Okay. Now this equilibrium actually helps us because here presence of bicarbonate ion and also H2CO3, both these are present, and it makes a buffer system. And this buffer system actually helps us to maintain the pH of human blood. Buffer system means that is, a buffer mixture means what? It means when you add externally some acid or base, obviously there is some limit, but up to a particular limit, if you add acid or base, the pH will not change drastically. It will always be maintaining a particular range. So as you can see in this case, for this buffer, the range is maintained between 7.26 to 7.42. And this is such a pH range where different reactions, that is biochemical reactions, that occur. Because mostly the biochemical reaction, they are enzyme catalyzed. And when it is enzyme catalyzed, particular pH maintenance is very important. If pH is not maintained, those reactions, that is enzyme cannot show its activity. So that is why pH maintenance is very important for those reactions, and this system actually helps us. This system remains in blood. Okay, so it helps to maintain pH of human blood in this range. Now CO2, it is anhydride of carbonic acid. So carbonic acid is H2CO3. You can write it like this. Now, why it says that CO2 is anhydride? Anhydride of something means what? When you remove water from this molecule, suppose you are removing one H, one OH. So what is the rest of the part? The rest of the part is CO2. So that is why CO2 is the anhydride of carbonic acid. That is H2CO3. How CO2 reacts with alkali? When the alkali, NaOH you can take as example, if it is very dilute, suppose you have taken some NaOH solution which is dilute and pH is lesser than 8, Now what will happen? There is water also present because it is dilute solution. So there is H2O. There is also NaOH. So CO2 what it will do? It will first react with water and it will form H2CO3 slowly. Now this H2CO3, see, CO2 is first reacting with H2, it is forming H2CO3. Now this H2CO3 is reacting with NaOH. The acid thus formed then reacts with alkali and it will give us NaHCO3. So this is basically acid-base reaction where only one replaceable hydrogen of H2CO3 is replaced by one sodium plus ion. Okay, we are getting NaHCO3. But if it is highly concentrated, suppose the alkali solution you have taken, it is fairly concentrated and pH is now greater than 10. Now CO2 will directly react with NaOH and it will form bicarbonate. Again it is forming bicarbonate, but now the reaction is different. And this is the first reaction, NaOH reacting with CO2, there is formation of bicarbonate. Now this bicarbonate, it can further react with one more molecule of NaOH and finally it is forming Na2CO3. So as a summary, we can say if you have taken dilute NaOH solution where pH is lesser than 8, your final product is NaHCO3. So only one H is replaced. But if it is concentrated NaOH, that is pH is greater than 10, highly alkaline, now the final product is Na2CO3. Though there is first formation of NaCO3, but finally we are getting sodium carbonate. So depending on whether you have taken dilute NaOH or concentrated, products will be different. Reaction with metals. Suppose you have taken some lighter metals like this, then it combines with CO2 and directly we are getting this salt. Okay, and there is also carbon as a side product. But if we take Mg, magnesium, now the product is different. Okay, so 2Mg plus CO2, we are getting magnesium oxide, not carbonate. Next, reaction with lime water. Now this reaction is very important because not just here, in other chapters also you will see some information related to this reaction. Reaction with lime water. Lime water means calcium hydroxide solution. When a limited amount of CO2, if we are passing it through CaOH solution, that is lime water, there is a milky appearance, and this milky appearance is because of the formation of the calcium carbonate. And calcium carbonate is not soluble, it is insoluble, so that is why it will appear as if it is milky. But if we are further passing more CO2 gas, there will be this milky appearance will be now removed and there will be generation, that is now it will be transparent again. So what is happening here? When excess of CO2 is passed through lime water, it is true that first there will be a milky appearance, but it will disappear and there will be clear solution. Now why we are getting clear solution? Because first there is formation of CaCO3, but when excess CO2 is passed, we are getting CaHCO3 whole. So once this compound is formed, milky appearance will not be there. So this is the reaction CaOH whole 2 plus CO2. There is CaCO3, and if this one CaCO3 is formed, we are again passing through some more carbon dioxide. There is formation of calcium bicarbonate. Now, if this is reaction number 1 and this is reaction number 2, suppose you are adding these two equations 1 plus 2. Now what will happen? H2O, here it is in the right hand side, here it is in the left hand side. So these two will be cancelled. So in the left hand side you will be, and also calcium carbonate will be cancelled. So in the final equation, if you add these two, you will get calcium hydroxide and plus 2 CO2, and in the right hand side there will be calcium bicarbonate. So this will be the reaction. If you simply add 1 and 2, you will get reaction 3. Okay. Reaction of CO2 with ammonia. Now it will lead to formation of urea, which is very important fertilizer. So we can say that CO2 we can use for synthesis or manufacturing purpose of urea. CO2 is reacted with liquid ammonia at this temperature 453 to 473 Kelvin. Pressure is very high, 220 atmosphere. It first forms ammonium carbamate, which is NH2CO2 NH4. So I can write this compound here, NH2, then CO, O minus, and this negative charge balanced by NH4 plus ion. NH4 plus ion is ammonium ion. So first there will be formation of this compound, which is ammonium carbamate. Overall it is neutral because there is one negative charge, one positive charge. Overall neutral. But subsequently this ammonium carbamate, it will not remain in this way. There will be formation of NH2CO NH2. So NH2CO NH2 is symmetrical structure like this. And water molecule is removed. As if this oxygen and 2H2 removed, and you are getting NH2CO NH2, which is urea, an important fertilizer. So this reaction, it can be considered as one of the application of carbon monoxide. We can use it for generation of urea, which is important fertilizer. Photosynthesis. So it is very important. All of us know this. In presence of chlorophyll and sunlight, CO2 is absorbed by plants. And once it is absorbed, now it reacts with water and there is formation of glucose, C6H12O6, and starch. And these glucose and starch are actually used as a food by the plants. And see, this is the reaction, 6CO2 reacting with 12H2O, and in the right hand side we are getting not just glucose. This process is important for formation of oxygen because we get oxygen for our survival only from this process. Fine. So we can say that green plants, it's not that they are converting atmospheric CO2 into carbohydrates and glucose, they are also producing oxygen. So plants prepare foods not only for themselves, it is also important for us, for as we are getting oxygen, and also from plants other animals are benefited as they can be used as a food. Now in case of CO, we have seen that it can bind with the hemoglobin. So when if it is hemoglobin is Hb, and when it make complexes with CO, this is very stable complex. It is also true that Hb complex with O2, but compared to HbO2, the complex between hemoglobin and carbon monoxide is more stable. So that is why in presence of CO, if we are in contact with CO, it is dangerous for us because this HbO2 complex formation will not be there, and as a result, oxygen will not be transported in every cells, and ultimately it will lead to death. But that is not happening for CO2. So unlike CO, it is not poisonous. But the problem is, another problem that we face from CO2, it is not deadly as CO, but what happens when there is increased amount of combustion of fossil fuel and there is formation of CO2. Remember, in the preparation part of carbon monoxide, we have seen how we can use fossil fuel combustion and we can produce CO2. But if it is happening in excessive way, then also another process is decomposition of limestone, that is calcium carbonate decomposition for cement manufacture, and that is in recent years. So these two processes that will increase the amount of CO2 in the atmosphere, and as a result it will lead to greenhouse effect, that is heat will be trapped in a certain layer of the atmosphere. Details of this you will be able to know in the another chapter, which is environmental chemistry. So because of this greenhouse effect, it will raise the temperature of atmosphere, and that is another lead to some serious consequence. So though it is not dangerous like CO, but if we consider in slow way, then this is also harmful for us. But that is in our hand, we can control it. If we can use this combustion process or decomposition of limestone for cement manufacturing in a limited way, then it is okay. Otherwise it will lead to greenhouse effect. Application part. CO2 is used extensively in preparing cold drink, soda and other packet foods. The fizzy nature that we get in soda, that is because of this trapped CO2 in the liquid. It is also used in fire extinguisher because it can stop the supply of oxygen. It is 1.5 times heavier than air, and that is why it can stop the supply. It can remove, because it is heavier, so it can remove the oxygen and that place can be taken by CO2 and ultimately burning process will be stopped. So as a fire extinguisher we can use it. Then solid carbon dioxide, obviously at a very low temperature, this is also known as dry ice. It is used as refrigerant. And dry ice, if we it is stable only at low temperature, but if you keep it in at normal temperature, obviously there will be dry ice will no longer be in dry solid form. So why it is dry ice? Because when, if you consider normal ice and when it is melting, it will convert it to water, liquid form. But when it is dry ice, because the solid form of CO2, it looks like ice, normal ice. It is transparent. It looks like normal ice, but normal ice will convert to liquid first at room temperature. But for solid CO2, which looks like ice, first there will be, sorry, it will directly be evaporated, which is known as sublimation. From solid directly we will get the vapor. So it is not, it will not melt. Okay, you will not get liquid CO2. So that is why it is dry ice, and it is used as refrigerant when very low temperature is required. And also there is some specific reactions that we want to do at very low temperature, then also dry ice helps us. Carbogen, which is a mixture of 5% CO2, 95% oxygen. It is used to stimulate breathing in the treatment of some respiratory disease. So this is a medical application. To produce inert atmosphere for chemical processing. Suppose you are doing some chemical reaction where oxygen, presence of oxygen is we do not want. So in that case, CO2 atmosphere can be used. In production of foam, in welding metals, that is joining two metal parts like iron, copper to prevent corrosion. It is used in the manufacturing of sodium carbonate by Solvay process. So sodium carbonate manufacturing, that is Na2CO3, that we have discussed in S block chapter, group 1, important compounds of sodium. So you can see there how we have used CO2. It is used along with ammonia in the manufacture of fertilizers like urea. So this reaction we have seen in the properties section of CO2, and CO2 can be used in the preservation of food grains, fruits. So when we want to preserve some food grains, fruits or any other food, we want to keep in an atmosphere where oxygen is not present. Now, what type of atmosphere you want to keep it? In CO2, because we don't want oxygen. So in that case, this gas can be used to preserve these food grains, because in presence of CO2 there will be no oxidation possible, and they can be in fresh condition for a long time. Here we have a problem which is related to solid CO2. Solid CO2 is known as dry ice, but why it is known as dry ice? So explanation I have just said. Remember, it is not converted to any liquid form. Directly there is sublimation. Now, what is the reason behind this statement? Why solid CO2 is called dry ice? Here, the first option is saying it melts at 0 degrees centigrade, evaporates at 40 degrees centigrade, evaporates at minus 78 degrees centigrade without melting. Now, this information is important. Boiling point is more than 199 degrees centigrade. Now, obviously, the third statement is the actual reason. It is not melting at 0. Because under normal conditions, CO2 it is in gaseous condition. So you cannot expect that just less than 0 degree it will be solid. That is true for water. When it is lesser than 0, then it is solid water. That is ice, but it is not for 0. And evaporation at 40 degree, that is also not true, because that means below 40 dry ice will remain in dry ice state. That is also not the case. Solid CO2 you can get only at very low temperature, something like this, because A compound which you are having the physical state under normal condition is gas. Obviously, when it is in solid form, just take the example of oxygen. If you want to get solid oxygen, the temperature has to be very, very low. So it cannot be 0 or 40. So it must be something negative temperature. So from that logic also, option C is the correct option. So dry ice is basically solidified CO2, which on solidification gives an appearance just like ice. Transparent nature is there. But it evaporated at this temperature, minus 78 degrees centigrade, and without melting. So directly it will be converted to the vapor form. And see, it is something like this. So in the spoon, it looks like ice, but actually it is not ice. So if we want to do any reaction, suppose we want to do any, especially in organic reactions, if we want to do it at minus 80 degree or minus 70 degree, then we can use this solid CO2, that is dry ice. Okay. Next question. Suppose you have to determine the percentage of CO2 in a sample of a gas available in a container. So there is a container, there is a sample of a gas, and we have to measure the percentage of CO2. Now, to measure this percentage, we need some absorbing material so that CO2 is absorbed to that solid material, and when the new material we are getting, that is after absorption. Now, if you know before absorption the weight of that material and after absorption the weight of that material, obviously by subtraction you can understand the amount of CO2. But which material we will use? That is the question. Which is the best absorbing material for the carbon dioxide? Now, even if you do not know this answer directly, just apply a simple logic. We know that CO2 is acidic oxide. When we have discussed the oxides of group 14 elements, there it is mentioned clearly, it is acidic oxide. Unlike CO, CO is neutral, but this is acidic. So if it is acidic, obviously it will have some affinity towards alkaline substances. Now look at the options. Heated copper oxide. Now this is oxide of copper. You cannot expect alkaline nature. Then cold solid CaCl2, calcium chloride. This is also chloride salt of calcium. This is not alkaline. Then solid calcium hydroxide. Now this can be an answer. There is also heated charcoal. Now even there is, if it is simply mentioned charcoal, then also it can be, you can consider it as correct answer, but it is heated. Now when you are heating it, obviously CO2 will be removed. Even if it is absorbed, it will be removed from charcoal. Fine. So that is why this is also not true. And we have also seen in the properties section of CO2 how it reacts with lime water. Okay. Now we have not taken lime water solution. We have taken solid calcium hydroxide. So it is solid, it is not lime water, because we are trying to absorb it. So in the solid form CaOH2, it can absorb CO2 because this is basic in nature and CO2 is acidic in nature. So these two can react with each other, not react exactly, that is, it can absorb it. Obviously there will be reaction and new compound we will get, but from the difference, or if we write the balanced equation between these two compounds, so from the calculation of number of moles, that is mole ratio, we will be able to determine the percentage of CO2. Okay, so correct option is this one, solid, cold solid calcium hydroxide. So the carbon part, that is all the important compounds of carbon, CO and CO2, that we have finished. Now we will start important compounds of silicon. Now under this, the first compound we have is silica. Silica is also having another name, that is, it is the common name that we use is silica, but you can also call it silicon dioxide, though it will not remain in this form. So if I am writing it as SiO2, it is just like CO2. Why I am saying just like CO2? Because if you simply replace C with Si, both are group 14 elements, right? So if you simply remove C with Si, you get SiO2. But this is not the whole structure. It is actually a network type of large structure but when we mention silica or silicon dioxide, in simpler way we can write this. So silica is an oxide of silicon. 95% of earth crust consists of silica and silicate. Now silicate is that will be discussed separately. Here just for information, see 95% of earth crust there is presence of silica and silicate. It occurs in several crystallographic forms. So silica, it can have crystallographic forms. It can also have amorphous forms. Now these three, quartz, cristobalite, tridymite, these three forms are crystalline. And these crystalline forms are interconvertible to each other at proper temperature. There is also amorphous form of silica. One is silica gel, another one is this one, Kaisergard. Okay, so you can get MCQ question related to this. So the first three, they are crystallographic form, and these two are amorphous form. Preparation, how we can make it. If we acidify sodium silicate solution, acidify, here we have taken sulfuric acid. It yields amorphous silica or precipitated silica. So precipitated silica or amorphous silica means it is in powder form. Okay, it is not crystalline form, so that is why it will be precipitated. So Na2Si3O7, though sodium silicate, it can you can also have another formula which is Na2SiO3, but this is also called silicate, because if you consider SiO3, it will also have two negative charge. If you consider Si3O7 anode, then also it will have two negative charge, and in both cases it is balanced by 2 sodium plus. So in the right hand side we are getting SiO2, silica, then sodium sulfate and H2O, but this is the actual compound we are trying to make. The second method is, starting from SiCl4, we can hydrolyze it. That means it will react with water. Not just tetrachloride, we can also take tetrachloride, that is SiF4, and we will get silicon dioxide. So here we are getting silicon dioxide, which is also associated with 2 water molecules. Third method, starting from silicic acid, SiOH whole 4. So SiOH whole 4 means there will be total 4 OH attached to silicon. Now in this case, if we do dehydration, then 2 water molecule. Suppose this is 1 water molecule, this is another water molecule is removed. Now you are left with this unit, which is SiO2, and the water molecules are attached to. Okay, though we can remove these water molecules, but when this reaction will occur, we will get it in this form. Okay. Next is structure. Now you can see it is not a single SiO2 molecule, because if it is so, then it will be just like CO2, but actually it is not. It is having this type of large network structure. Okay. If you focus on any one particular silicon atom, you can see there is total 4 bonds, 4 sides with the oxygen. And if you focus on any particular oxygen, it is linked with 2 silicon both sides. Fine. Now, though it is shown in this way, but don't think it is planar. The environment is basically tetrahedral. Surrounding silicon atom, there is tetrahedral arrangement. So it is a covalent molecule, but silicon atom is tetrahedrally coordinated in the bulk of silicates with 4 oxygen atoms. Why we are saying it is silicate? Because if you consider a single unit, suppose if you are breaking this and if you are on this unit, it will be SiO4 minus. So that part is silicate, that is the anionic part. If you consider the whole part, you can call it silica. But in the bulk of silicates, that is several silicate units with 4 oxygen atoms around a core silicon atom, which is clear from the picture. And if you focus on a particular oxygen atom, it is bonded to 2 silicon atoms. So the silicon dioxide has a large structure, and the ring that we are having, it is 8-member ring, total 4 silicon atoms, total 4 oxygen atoms. and each corner is further shared by another tetrahedron. So if it is one tetrahedron, then another tetrahedron is left hand side and also right hand side. So as if all these tetrahedrons, they are linked to each other. Okay. The empirical formula will be determined by the smallest ratio of atoms in the structure. So though there is a large structure, but if we consider the smallest ratio of atoms, suppose you know the total number of silicon, you would also know the total number of oxygen. So if now we take the ratio of it, it is observed that 2 oxygen atoms are present for every single silicon atom. That is why the empirical formula we always use to express it, because that is easier to do, and it is SiO2 per silicon, 2 oxygen atoms. Entire crystal may be considered as 3-dimensional network solid. So though it looks as if it is planar sheet, but it is not planar sheet like structure, it is 3-dimensional network type of solid. And one more information, the structure of these two obviously entirely different. CO2 is single molecule, right? See both sides there is double bond. But here SiO2 is not a single molecule, it is completely different. Now these two structures, if you consider, these are actually example of double bond rule. It says that when you have any element with principal quantum number greater than 2, so for silicon it is from third period. So if you consider the valence shell, it is 3s2 3p2. For carbon, it is 2s2 2p2. So for elements with principal quantum number greater than 2, for their valence electrons, that is, if you consider silicon valence electrons 3s2 3p2, total 4 electrons, they tend to form multiple bonds. Okay. Sorry, not tend to form multiple bonds. So if it is lesser than 3, that is 2, if it is 2, then it will form multiple bond. So here in case of CO2 you have multiple bond, that is pi double bond between carbon and oxygen, but that is not the case of Si. So don't think that the bonding is like this, it is absolutely wrong. So it is because of double bond rule, though the we are saying that it is double bond rule, but actual logic is silicon is from third period. So when it is forming trying to form pi bond with oxygen, it is difficult because then it is sidewise overlapping of 2p orbital and 3p orbital, so which will not be very effective. But if the pi bond is between 2p, it is more effective because 2p is more compact in nature compared to 3p. So this is the actual reason, but it is known as double bond rule, which is elements principal quantum number greater than 2, for their valence electrons, they will take part, they will not take part in multiple bond. So that is why we are having completely different structure for CO2 and SiO2, though both the elements are from same group 14. We will end the session here. Thank you for listening.